Hey guys, long time no see. Today's video will be on something a bit different, and it will be part of my differential equations series, and this one will be on first order linear differential equations. Yeah. And this first lesson will focus on how to solve them using integrating factors. And yeah, okay, so first thing is that so the form of first order linear differential equations is, well, there's actually two forms, but the first one is p of t times y prime plus q of t times y is equal to g of t. And for this lesson, I'll actually be using the other form, which can just be obtained by dividing these by capital P of t. So the second form is just y prime plus lowercase p of t times y, which is just q of t divided by capital P of t, by the way, and which is equal to lowercase g of t. So in this video, I'm going to cover how to solve these types of equations, which aren't like obviously separable. I mean, separable ones are pretty intuitive, but these ones are a bit tricky. So basically, how integrating factors work is actually, let me just start off with an example. So actually no, okay, so just to give you an idea of how they work, let's say we have the following problem. So you have t squared y prime, let me see, okay, plus 2ty, and that is equal to t cubed. And now something which most people do, and usually this is a good idea, is to divide by t, right? Because it's common in all the terms. But actually, in this case, that would be a bad idea, and it would unnecessarily make the problem a lot harder, if not impossible, to solve. So instead, if you look very carefully at the left side, you'll notice that 2t is the derivative of t squared, and y prime is obviously, by definition, the derivative of y. So you can see that this is actually a product rule differentiation. So now we can actually rewrite this if we know like what this is the differentiation of, and just looking at it, it appears to be the differentiation of t squared times y. So we can rewrite the left side now as the derivative with respect to t of t squared times y, and the right side is still t cubed. And now we can simply just integrate both sides. So to do that, we have the derivative with respect to t squared times y times dt, and this is equal to t cubed times dt. And if we integrate, we just have t squared times y is equal to t to the power of 4 over 4 plus c, which means then that y is simply just dividing both sides by t squared, so y is equal to t squared over 4 plus c over t squared. And boom. So what initially looked like a hard equation to solve and something that wasn't obviously separable can actually be solved just by noticing that the left side is simply a product rule differentiation. And yeah, so that's kind of how integrating factors work. So I'll just erase this example. Oh dang, okay, I accidentally cut that off. Okay, nice. Okay, so let's do another example. So now, actually, let's derive a formula for the integrating factor. So let's say I have some equation, which is y prime. Well, I'll just make it the second form. So it's y prime plus lowercase p of t times y, and that's equal to g of t. And yeah, so basically, as I said in the previous example, the integrating factor should be such that if you multiply to the whole equation, the left side of the equation would be a product rule differentiation. And the integrating factor is, the symbol for that is mu of t. So this is the integrating factor. Okay, so yeah. So now let's multiply this entire equation by mu of t. And if we do that, we get mu of t times y prime plus mu of t times p of t times y, and that is simply mu of t times g of t. Okay, great. So as I said earlier, we wanted so that if we so that this whole left side of the equation is a product rule differentiation, and we can see now that just like for the previous problem, y prime is the derivative of y. So for this to be a product rule differentiation, mu of t times p of t has to be the derivative of mu of t. So now let's write that down. Okay, great. And just to make it simpler, I'm going to rewrite mu of t as d mu dt, and I'll just write mu and mu of t and p of t as mu and p. And yeah, and so now all we have to do is integrate, and we get d of mu over mu is equal to the integral of p of t times dt. And this would just be the natural log of mu of t. So we can see that mu of t has to be positive, otherwise it's not going to return a value, because you can't take the natural log of 0 or a negative number. And yeah, so this is just equal to this. So then we can see then that, I'll just draw an arrow here, the integrating factor, mu of t, has to be e to the power of pt dt. And this, since we use the general form of the second equation, this applies for any first order linear differential equation that's in this form. And if it's not in this form, then we can just convert it from this form to this form. And yeah, so without further ado, let's try an example, or actually let's try a few examples. Okay, so let's say we have some equation that is t times y prime plus t plus 1, or the quantity of t plus 1 times y, is equal to t times e to the power of negative t. And t, let's say t is greater than 0. And so we want to solve for y in terms of t. Great. Okay, so So as I mentioned earlier, the general form is just y prime plus p of t times y, and that is just equal to g of t. And since y prime isn't by itself, all we have to do is divide both sides of this by t, and we should get y prime plus t plus 1 over t, or if you want you can simplify it. But as you'll see later, there's actually no need to simplify it, and it's actually easier not to. So yeah, we have this, and then this is just e to the power of negative t. So then we can see now that this fits into this form. So then we know that this is p of t, and this is g of t. And we can just find the integrating factor using the formula I derived earlier, which is that mu of t is simply equal to e to the power, and this is just the same thing as e to the power of something. So e to the power of p of t times dt. And in this particular case, that would just be 1 plus 1 over t dt, which is t plus ln t. Oh wait, and this is supposed to be e to the power of, so it's actually e to the power of t plus ln t plus c. Oh, actually, and also let's make this an initial value problem so that we can actually solve for c. So let's say y of 1 is 1 over e. Okay, so if we wanted to solve for c, all we have to do is plug this in for y, which we will find after we find the integrating factor. Okay, so so actually using the properties for exponents, we can actually just multiply this all out. And if we do that, let's see. Actually, for now, let's ignore the c, and we can find it later. So for now, we have e to the power of t times e to the power of ln t, which is just t times e to the power of t. Okay, so yeah, that's the integrating factor. So then we just plug this in to the original equation, and so by plugging it in, I mean we multiply it to the whole original equation. So yeah, and if we do that, we get, actually we multiply to this equation because this is the proper form. So if we do that, we get t et y prime plus t plus 1 et times y, and then we multiply to this, which is just t. Whew, okay, nice. Let me just double check. Okay, so then yeah, and then so this, if we use the same thing we used in the previous problem, or the same way of thinking, we can see that this is just the derivative with respect to t of t times e to the power of t times y. And so we can integrate this and set, actually, and then just dt here, set it equal to the integral of t times dt. And if we do this, we get t times e to the power of t times y is equal to 1/2 t squared plus c. So now we're bringing back c, because now we can use this to solve for it. And if we do that, so we plug in 1 for t, so this is just ey is equal to 1/2 plus c. And y is just 1 over e. So then we get that c is just 1/2, which means that this is t squared over 2 plus 1/2. And to solve for y, we just have to divide both sides by t times e to the power of t, so we get that y is equal to 1 over t times e to the power of t of t squared over 2 plus 1/2, and the t's cancel out here, which gives us t squared plus 1. Actually, well, there's two ways to do it. So you could either write it as t squared plus 1 over 2 to the power of et, or if you prefer, you could just cancel out the t's here and get t over, oh wait, there is a t here, okay, t over 2et plus 1 over 2t et. And yeah, so that is how you solve a seemingly tricky first order linear differential equation with the integrating factor. And one important thing to keep in mind that I almost forgot is when you're solving for the integrating factor, ignore c, and you can solve for c later. So yeah. And I'll just do some more practice problems, mostly for my benefit, to get more accustomed to this. Okay, so let's say now we have some equation y prime plus 2y, and let's say that's equal to t times e to the power of negative t plus 1. Okay, so as I mentioned earlier, the general form we want is y prime plus p of t times y, which is equal to g of t. So in that case, we I wonder if it's necessary or not to divide by t. Actually, I'm gonna try. Okay, so I'm gonna try solving this first without dividing by t, and then with dividing by t, because I'm actually genuinely curious to see if it makes a difference. Okay, so yeah, let's try it first without dividing by t. So then I'm not going to change this equation at all. So then p of t is just 2, which means that the integrating factor is just e to the power of the integral of 2 dt, which is just e to the power of 2t. Actually, I think it might work either way. I don't know, we shall see. So, okay, so then we just multiply e to the power of 2t to the whole equation. So we have 2 e to the power of 2t times y, and this is equal to e to the power of 2t times t e to the power of negative t plus 1. And this is equal to t times e to the power of t plus e to the power of 2t. Okay. Okay, I don't think I made any mistakes. Okay, so I think, yeah, I don't think it matters whether or not you divide by t on both sides here. But one way might be easier to solve than the other, and another might be harder, so yeah. Okay, so next we want to integrate. Actually, wait. So yeah, this should be the derivative. Okay, so I said that y prime is the derivative of y, which means that 2e. Oh yeah, okay, so this whole thing is just the derivative with respect to t of e to the power of 2t times y. And we want to integrate this and multiply dt, and then this is equal to this side, which is just t plus e to the power of 2t times dt. And so this whole thing is simply just e to the power of 2t times y. And we have to integrate this, and okay, this actually looks like it's going to be a pain because I think we have to use integration by parts. Actually, no, I think we could do substitution. So let's say u is equal to et, which means du is equal to et dt, which is u dt. So dt is equal to du over u. Okay, so then, and then t is just the natural log of u. Actually, no, either way, I would have to use integration by parts. That's interesting. Actually, I think for that reason, it's just easier if I divide by t. So, just to get some practice anyways, I'm just going to redo this whole thing, but instead I'm just going to divide by t, because I'm too lazy to do integration by parts. Okay, so if we're dividing by t, we get from this equation wait, actually, oh no, I can't divide by t because it has to be y prime by itself, which means I just erased all my work for nothing. Fortunately, I have the undo button, so I'll just... Okay, so yeah, it turns out I actually have to go through the pain of integrating that. So then this is e to the power of 2t times y. And, okay, first I'll integrate this, I guess. So, okay, so the integral of t et dt. And so I'll just say that oh no, I can just use the tabular thing. Okay, so u dv. And in this case, u will be t and dv will be this. Okay, I'm a bit rusty, so I hope I don't mess this up too badly. Okay, so that's u, and du would then just be 1, and the second derivative of u would be 0. And okay, how do I do this? So this is plus, actually this is plus, this is minus, and this is plus, but this is 0, so we don't care about this. Okay, so then the integral of this is just e to the power of t, and the integral of that's e to the power of t again. So we have t times e to the power of t minus e to the power of t. Yeah, that sounds about right. And then e to the power of 2t is just 2. It's just 1/2 times e to the power of 2t. So then I'm just gonna scroll down. So then this huge mess here is equal to t times e to the power of t minus e to the power of t plus 1/2 e to the power of 2t. And this is equal to this. So then to solve for y, oh, and also plus c. Almost forgot. Okay, so to solve for y, we just divide both sides by e to the power of 2t. And so this is t times e to the power of negative t now, minus e to the power of negative t plus 1/2 plus c. Or you could just turn it into plus c, since 1/2 is also a constant. Okay, and let me actually just clean this up a bit. So we can rewrite this as t minus 1 times e to the power of negative t plus 1/2 plus c. And wait, 1/2 plus c. I think I messed up somewhere. Okay, let's see. Oh yeah, I think actually I was supposed to divide c by e to the power of 2t as well. So this is c times e to the power of negative 2t. So actually we don't, you can't combine the 1/2 and c actually. Okay, so that should be the right answer. And okay, so let's try another practice problem. Okay, now this one is going to be an initial value problem. So now we can actually solve for c. Okay, so let's say we have, okay, let me just clear everything. Okay, so let's say now we have t times y prime plus 3y is equal to t squared minus 4t plus 1. And since it's an initial value problem, let's use y of 1 is equal to 8 over 15. Okay, so now we want y prime to be by itself, so we have to divide by t. And if we do so, we get y prime plus 3 over t times y is equal to t minus 4 plus 1 over t. Okay, and recall that this would be g of t, this would be p of t, and if we want to find the integrating factor, that would just be e to the power of the integral of p of t times dt, which is just e to the power of 3 times dt over t. Or in other words, e to the power of 3 ln t, which is also e to the power of ln, or the natural log of t cubed, which is just t cubed. So our integrating factor should be t cubed. Okay, so let's multiply that to this equation, and we get t cubed y prime plus 3t squared y is equal to t to the power of 4 minus 4t cubed plus t squared. Okay, nice. So now, okay, so now we have to see like which term this is the product rule differentiation for. And just looking at it, we can see that it's just the same thing as the derivative with respect to t of t cubed times y. So then now we integrate this and set it equal to the integral of this side, which is just t to the power of 4 minus 4t cubed plus t squared dt. And now we get t cubed y is equal to t to the power of 5 over 5 minus t to the power of 4 plus t cubed over 3 plus c. And unlike in the last problem, they gave us this parameter so we can solve for c. And to do this, we just plug in 1 for t, so we get y is equal to 1/5 minus 1 plus 1 cubed, and y is just 8/15. So we set this all equal to 8 over 15. Okay, so then this is 3 over 15, this is 5 over 15, minus 1 plus c. These two have to cancel out, so c is just 1. And so we get that y is equal to, okay, so we just divide both sides by t cubed and replace c with 1, and so we get t squared over 5 minus t plus 1/3 plus t to the power of -3, or if you prefer 1 over t cubed. And yeah, so it's t squared over 5 minus t plus 1/3 plus t to the power of -3. Okay, yeah, so that's basically the gist of using integrating factors. So you use it in equations that don't seem to be separable. And yeah, so I hope you found this video helpful, and peace.